Okay, hello everybody. So this is going to be the last lecture on chapter 4. This section is going to deal a lot with starting to talk a little bit about chemical reactions in organic chemistry. And most of this is talked about after the first exam when we get to chapter 6. But I wanted to kind of bring this on board now because it is talked about in this chapter, and I think it is worth knowing a little bit about what's going on. So one of the ways that hydrocarbons, alkanes, can be made in particular is through the process of hydrogenation. So hydrogenation may have been a word that you've heard of before. If you've ever read the back of a margarine container, it'll say you have partially hydrogenated oil. And what hydrogenation is it's essentially a way to convert carbon-carbon pi bonds into and add hydrogen to them and turn everything into sigma bonds and add hydrogens in place of where those pi bonds are. Now, that cannot be done without the use of a catalyst, which lowers the activation barrier to make the reaction happen. And so typically the metal catalysts that are used, there are several. Platinum is very good, but it is extremely expensive. Nickel is also quite good, but it is very toxic. And probably what is most commonly used is a mixture of palladium on carbon. Now, palladium isn't very cheap, but it can be ground up very well with charcoal, and you can make like a 10% palladium, 90% carbon mixture, which does a very good job and isn't very expensive. So what this process essentially does is if you have a hydrocarbon like this one here, where you have an alkene, where you have like cis-butene, and you have hydrogen atom or hydrogen molecules in there, it won't react with it. But if you were to add some of these metals to it, the metal actually helps to activate the hydrogen to make it more reactive, so that the hydrogens start to add in place of where those pi bonds are, and it starts to break their the sigma bond in between them. So what you end up with is essentially adding in hydrogen to where there was a pi bond. Now, hydrogenation is useful, but one of the problems with it is it's not extremely selective. So if you were to do hydrogenation, and I'll just show a different metal here, and you have two alkenes, it will actually go after both of those alkenes and will hydrogenate them. So typical aliphatic systems are going to undergo what we call full saturation. And that also includes alkynes as well. And in fact, since there are two pi bonds that are present in that system, that means hydrogen will effectively add twice, okay? So as long as you have enough hydrogen gas in there, and really even if you were to limit it, it's not going to give you, it's not just going to reduce it to the alkene and be done, because what will happen is you'll get some alkene will go on and react to the alkane, so you'll get a mixture. So it's not very practical to try to limit this with stoichiometry. There is a way to only get it to add one round of hydrogen, but you need another catalyst to do that, and we're going to talk about that in the future. So what you want to be careful though about is when you draw out that product, that you want to make for sure that you're not losing any carbons or putting any extras in there. And so between 2 and 3 now, you're going to be adding essentially 2 sets of hydrogen atoms in there, would add in twice. Now, the one system that is pretty resistant to this is benzene. Benzene, if you try to do this under normal conditions, and what I mean by that is 1 atmosphere of hydrogen, that's not going to cut it. You can get benzene to react if you use a very high pressure hydrogen and heat it up. So Benzene aromatic systems, aromatic hydrocarbons are very stable. And so they are not going to do what your typical alkene system will. Why won't they do it? Well, see me in Organic 2 for more details about that. But I wanted to at least mention it here. Now, one of the ways that you can actually look at a molecule and talk a little bit about, what's going on in that system is to look at what it's called its index of hydrogen deficiency, or its IHD. Now, what that is the difference in the number of pairs of hydrogen atoms between the compound being observed and the fully saturated acyclic alkane system, which we've already said before has this formula CnH2n+2. So for instance, if you were going to look at these two systems here, so both of these are isomers of each other. So this is a C5H10 and this is a C5H10 system as well. Now this is one pentene, and this is obviously cyclopentane, but they both have the same chemical formula. Now, one of the things that we can say about both of these is that if you were to consider the fully saturated system, both of them have 5 carbons. Well, if you apply the formula 2 times 5 plus 2, the fully saturated system would be C5H12. Whereas the compound that's being observed, which are these guys, is C5H10. So that means you have a pair of hydrogen atoms that's different here. And that is what an IHD is. So that is one pair of hydrogen atoms that we are considering. And so both of those molecules have an IHD of 1 associated with them. Now, for each IHD in a hydrocarbon, that indicates a ring or a pi bond that's associated with that system. Now, obviously, not everything is a hydrocarbon. So for other atoms of interest that we're going to be looking at here, one is if the molecule contains oxygen, well, you can just ignore that oxygen and just play like it's not even there. Treat halogens like hydrogens when you're calculating your IHD, and subtract 1 hydrogen for each nitrogen in the system. Okay? So with those rules in mind, we're going to try to calculate some IHDs. Right? So we'll start with the one on the left, and you can try this too. Okay, so if you want to calculate the IHD of this system, the fully saturated system, you have 6 carbons, so that's C6, H2 times 6 plus 2 is 14, so that's your fully saturated system. And then the actual chemical formula of the compound itself is C6, 1, 2, 3, 4, 5, 6, 7, 8. No hydrogens here in that triple bond. Well, that's going to be a difference of 6 hydrogens, which is going to be an IHD of 3. Now, does that make sense? Yeah, you have 3 pi bonds, so that's why you have an IHD of 3. Now, what do you think the IHD of this system here is without doing the math? What do you think it would be? Okay, and if you said 4, you're on point here. Okay, so this compound fully saturated is also C6H14. Okay, but as it stands at the moment, it's 6 carbons and 6 hydrogens. And so that means a difference of 8 hydrogens, which would be an IHD of 4. And that makes sense because you've got 3 pi bonds in a ring. And so that's where you get the IHD of 4. Okay, so what do you guys think about this guy? Okay, and if you said 3, you are correct. So this system here is C4H4O. And so we said to treat that like it didn't have oxygen, so we'll treat it like C4H4. And the fully saturated system would be C4H, 2 times 4 plus 2 would be 10, and that would be 6 hydrogens, and so an IHD equal to 3. All right, which would be the ring and 2 pi bonds. Okay, what about this guy over here? All right, if you said 0, all right, but then that is correct. There are no pi bonds and there are no rings. So its chemical formula is C4H8Cl2. So each chlorine and each halogen we're going to treat like hydrogen, and we're going to treat that like C4H10. So the fully saturated system would be 4 hydrogens, and 2 times 4 plus 2 would be 10, and so a 0 there for your IHD. Okay, and then what about this thing down here? Okay, so this is actually, I picked a natural product, and so this is the compound nicotine, active ingredient found in tobacco products. So it has a chemical formula of C10H4, H14 N2. C10H14N2. Just verify that. Okay, it's got 2 nitrogens, so that means we should treat this like C10H12, subtract 2 hydrogens from that. The fully saturated system would be C10H22, and so the difference of that would be 10 hydrogens, which would be an IHD equal to 5. And so you've got 2 rings and then 1, 2, 3 pi bonds, so an IHD of 5. Okay, that may seem kind of trivial doing that, but that is actually kind of useful when you're trying to elucidate structures of unknown molecules, like this question right here. Okay, so this is going to be the last problem that we're going to do in the chapter. So you were told you have an alkene and it has a chemical formula, an alkane that has a chemical formula of C6H14. It can be made from hydrogenation of only 2 precursor alkenes, which have a chemical formula of C6H12. Determine the structure and names of all the reactants and products. Okay, now this seems like a really difficult question because it doesn't give you a lot of information. But if you remember your IHD rules here, you can see right away that the C is a fully saturated system. So that means C, it's not a ring that's in that particular compound, okay? And if you look at the 2 precursor alkenes, well, they're indicating an IHD of 1. Which means if there's no rings, it has an IHD of 1, well, then that means that both A and B have only 1 pi bond in them. Okay, so now we've kind of got a little bit of some headwind here. So now we just kind of got to play a little bit of a thinking game here. So the first thing to consider is well, what if C was just a plain old hexane with 6 carbons, okay? Well, if it was a plain old hexane, if there's only one, again, remember there's only 2 compounds it says that could make this, well, I could have the double bond here, or I could have the double bond here at the number 2 position, you know. And I could also have the double bond the number 2 position, and I could draw this trans, 1, 2, 3, 4, 5, 6, and I could have the double bond at the number 3 position as well. So, okay, we're already up to 4, so we can pretty much rule out that C being that compound. All right, so let's say we put a branch into it. Okay, so we branch it a little bit, like so. Okay, well, now you could have the double bond at either one of these 2 carbon positions, which would be equivalent. You could put the double bond here or the double bond there. That's the same thing. You could also have the double bond here, but you could also have the double bond here, or you could have the double bond all the way out at the end. And so, and then I'm not even bringing in the trans possibility here. So again, not really too many possibilities. Okay, so let's try another one. Let's say that I try to branch this a little bit more. Okay, and that kind of looks symmetrical, and so that's kind of what we want if we're wanting a system that there's not a lot of possibilities. Now, if I put the double bond at any of those carbons, like here, 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 or here, every single one of those is equivalent. Okay, so there's really no difference because all I need to do is rotate around sigma bond and you would get that structure. Okay, so there's one possibility here for making that compound. And you could also potentially make that if the double bond were in the middle, like so. That would also work. And really, that's it. So we found our molecules. Now, can we name them? So start the numbering again. Make sure you give the alkene the lowest possible number. So the one on the top is 2, 3 dimethyl 1-butene. The one on the bottom is 2, 3 dimethyl 2-butene. And compound C, which is over here, is 2, 3 dimethyl butane. Okay, so that is this is a little bit shorter lecture to make up for the very long lecture that we just had, but that's a nice little introduction to hydrogenation and how we can use that to kind of help with index of hydrogen deficiency and to determine unknown structure. Okay, so that gets us through the end of chapter 4. So guys, I will see you all in the next video. Everybody take care, and bye-bye.